as well. So when you zoom in with electron beams, you will discover the green structure, which is random. Moves on. So natural rocks are heterogeneous material, toilet paper, and this can be observed by microscopes. Tennis fiber reinforced composite materials. So when you and look at observe the material, and the carbon fibers, they are embedded in the resin matrix. Timber is typical heterogeneous material, very easy to observe the structure just under microscope. Plastic, including homogeneous, even glass, it looks transparent. It may surprise you when you zoom in microscope. It's become heterogeneous as well. To an extent, everything is when you talk about materials. So what is heterogeneous material? It's a mechanism for multiple materials, including voids. And this is an example of the bread matrix and bread randomly distributed. To investigate or to understand or to predict the behavior of contact is treating the material as a body. It could work, especially if you are talking about the structure of I-beams, for example, steel I-beams. You're talking about bridge behavior. Yes, it's made from rubber bridge is several kilometers long. At that scale, need to consider of the material. But in many other, it is necessary and critical to consider the homogeneity of the materials, especially if you are material to its limit. So in aerospace industry, where you do push the boundary capacity as much as you can. How do we observe the materials? It's quite costly. The easiest one, optical microscopes, timber can be observed easily. With equipment, but not anymore. It's very similar to the hospital. So that's the cost we are talking about. The only industry X-ray that you use to scan material is more powerful, but essentially the same concept. Is a desktop SEM may cost you 200,000 yuan. Go up the scale to have larger one, but in fact it's quite wide atomic scale, which is still quite expensive and it's typically accessible, only accepted from microstructures of materials. It's no longer an issue. That's no longer a technical hurdle. These pictures image simply shows an example of so-called polycrystal structures, and these are all micromaterials looks like steel. Even try to predict the price of materials. Let's treat all materials. There are different courses and many other scientific and engineering topics. Maintenance typically use experimental approach to extent like cooking in the kitchen. You mix materials, slices, and test after it's cooked. One way of treating that from the competition requires typically 3 steps. The composition using the microscopic imaging techniques, which we had in the previous slides. From there, know the composition and know the microstructure material, you can then try to construct the structure. Construct a 3D model for But imagine you are doing that for something much, much smaller in microns or nanometers. Last step is to do physics-based simulation. Know the morphology, the geometric properties, performance of your material. So this, I'm going to have a bit of in this talk. We start with the easiest one. We call that the addition of heterogeneous material. So simple diagrams shows what hydrogen is like, or all materials what it looks like. And black, randomly distributed across your medium. To capture, so I would be finite number of faces, so you could use integer to I is of course space, because the random of this I is of course random as well. So then it's location and it's random for a random field. 2D, if you're talking about 3D material, it's a 3D. So how do we quantify this random field? This is a 100 by 100 pixel. So you would have 10,000 random variables here. That random field, just in 2D, much of your mathematical capacity, unless you start to introduce a sample. The whole field is Gaussian, then you only need two parts. But that's very rough, very brutal. Material is Gaussian for a fact. So in practice, what engineers and researchers have been doing, thinking too much about the random field. They introduce so-called statistical description to capture the find manner the features of microstructure morphology. So what is statistics? The easiest would be like, so you might say, I have 3 faces, but you might even say, okay, so finding 2 points of material within different phases, the correlation between them. Things like this. Depending on the people have defined different statistical descriptors. Visibly from, I'd say, oil and gas sector, they deal lots and they have money. So about 40 to 50, where people the hydrogen material structure is metalloids in particular. When you zoom in, you see greens, they are random as well. It's more complex than that. In fact, not just random, it's a high dimensional. Chemical engineering, even tissue engineering in they have defined their own. Say we have the statistical descriptors. None of these work. Individual have to put them together, take a combination of them, and even give you a comprehensive quantification of your random field. The way to capture random field comprehensively is to go for probability distribution, or use structures. Let's say if it's a one-dimensional thing, which again very never work with material. So to move on, I'm going to give you just a few statistical descriptors. These are easy to understand. The volume fraction is a ratio between one phase and the entire volume of your material. You could have the so-called specific surface area. Surface area per unit. So it's another ratio where you have a surface area per unit. It kind of tell you Similarly, you can do something more mathematical because the functionals M2, they are identical to fraction and to special surface area. You have your M3 here as well. 1, 3 is basically an average. Some of you might be familiar with this. Geometry is you integrate the curvature and over the volume. What is this? This is a green set distribution. This is so you have inclusions of this. If somehow you define the set, you can define that. It is of course a so the distribution of that size itself becomes as a statistical descriptor. But then the question, how you define the size of your inclusion? The power size distribution, which is rather similar to the distribution. So how would you define? Say a power looks like this. You can of course make paths in the power. Say about the power size, you can in the power with spheres or largest diameter or radius of your sphere. You could also do something like this. The effective diameter by using the area and treating that as effective. So there are different ways of defining the size of your grains. Therefore, that changes as well, etc. And when correlation function by picking more points in your the more points you pick, the more data you will need to calculate that indicator. Endpoint correlation I mentioned here. Linear path function is another interesting one. And a linear path falls in the same phase with, so that tells you how well connected your materials is. And this is some materials, say porous material in particular, the connectivity between phases. Water, understand water, how water passes through your sponge. So direction of your pore space doesn't help. You need to know how, and that's where the linear path function comes a role. So we have many of these descriptors. Some of the one, most of them have mathematical, but in reality, you only have about descriptive equations, and the other 100 plus have no equations at all. What they, how they are defined is basically an algorithm. Size the image could be 2D, could be 3D. With a step, and that algorithm give you that vector is your so the fact is are defined in different ways. A small percentage of them, and they are not in most cases dependent from each other. So each of them captures certain aspects of the statistical information for your material, could be geology, but surely they are not independent from which one to use. We have 150 of them, which one to use, and why you use certain of these descriptors. And simply, there was no answer to that question. A few rare cases where you can mathematically derive the relationship between factors, but other than that, it's unknown, unanswered question. The question is important because we want to use this to characterize the materials, combine them. Surely you shouldn't use all of them. Many of them also because some of them over strongly. If you use those overlapping descriptors, descriptor introduce information conflicts. So we did a piece of work, quantify or quantitatively understand between descriptors. This is achieved by using two or AI methods, and this was only done, you might say, after 50 plus years of development in different fields. By proposing only until recent years, this question was solved. So what is the question? The question is the descriptors. Some of them are just one number. Some of them is a vector function. So we want to understand between all these descriptors. This is a typical, say, if we treat this question from a data, the challenge data is not of uniform format. They are of different lengths, genus data. How to understand the relationship between genus data. When we realize, we start to think, can we regularize the data set, meaning convert them to, and then if we can do so, we manage to do so, we end up with a much larger data format, because this uniform data format has all these 150, 200 plus which is not analyze dimension reduction to make that available. And finally, we can do feature analysis on the reduced dimension data set. How we did it. It took the solution, but once it's done, it's quite simple. This is what we have. This is what we have. We have these descriptors represented by D, and they are of different lines to handle them. So what we did here is that descriptors is defined to quantify like this. Could be 2D, could be 3D. So we pick a set of, let's say 1, just as an example, each formats. We can't analyze them. We use each individual descriptor as a guide to reconstruct a synthetic image. Only particular descriptor as the target or objective function. Then we constructed images, the whole set, for each set of them, because we only use the descriptor as the target to do the action. Therefore, the resulting image only information or a partial of the original image, and that partial information is directly determined by that descriptor. So the logic here is we synthetic image from the reference, one guide, and that one guide to use that descriptor individually to minimize the difference between the original one and the measure of that one descriptor. We end up with a set of results. Results only contain a partial information for the original image, and that part is captured by that chosen descriptor. So what we then did is construction algorithm, the same optimization technique to build many sets of each set of them correspond to one descriptor. So then we say the result data sets, the resulting data sets, each set capture the statistical information descriptor, which is also linked to reference image. So again, it's biased to that original reference image. To that by take multiple random images from different type of to make it more generic. But the logic. So how did we do the reconstruction to capture only the picture, and nothing else? Well, we start with a random guess distribution, and then we have our target. Each time we try to swap the pixels. For each swap, we check if this swap to that target measured by which is defined by that chosen descriptor. Continue that iterative process until so by doing this, the loss function smaller and smaller until it reaches threshold. At that point, we end up with a final realization which it contains information, no more, no less, measured by that particular, which is that particular descriptor. So we could check the accuracy of the process. So after we obtain synthetic images, have the difference between them, and indeed, the descriptor quite accurately. So we basically have all descriptors in the form of an image, and they are of the same size, same dimension. So it's a uniform. Then the question becomes, okay, forget about descriptors, a bunch of images. So the question is that quite common computer vision problem to classify or cluster these images to find them. There are, of course, many different methods of doing this. We did this. We are less knowledgeable what we are now about computer vision. So we use a basic method, which I have some of the details here now. We clustering but to dimension to map this smaller vector, and we did that by using extra spectrum. So the result is something like this. We map each image to a vector, which is 12 dimensions. They are of that particular image, and we cluster these points in this hyperspace is 512 dimensions. So this is the clustering process, just as an example. The final outcome is quite simple. Outcome is in this work we did 40. So if you group descriptors into 41 groups, you end up with descriptor in each class easy. If you group these 41 groups, what you want to do is grouping such a way that descriptor in the same group are more similar to each other. Just in different groups, they are more different from each other. You group them based on the similarity. And similarity was done or solved through k-means the distance between the feature points in the hyperspace. We have done this from 2 groups to up to 15 groups. So we might well say group clustering. All the descriptors are similar to each other, and all B between A and B they are visible. We can see of our grouping based on known conclusions and agreeing with each other very well. The relationships between the descriptors because they have a mathematical representation, and we found all exist covered from that grouping. Okay, so that's the easiest bit of the talk. I'm afraid I will skip or accelerate a bit, and this is even if I spend more time in the next 2 sections, you will get lost. Not by means of equations, but by physics involved. Is we can characterize how we could build the microstructure without physics-based simulation or physics-based. And this is a question that has been researched for decades, I should say. What people is taking directly from microscopes and use that as a structure. At least for 2D, if you have an X-ray CT, you can even do the structure just from the scanning image. The limitation is, of course, availability, the size and the capacity of your equipment. Not because of the randomness of these structures, you always need ideal structures, and you need large structures. Gain a statistical representation for evaluation. Alternative way of doing that is you do digital. So you take the scan as your reference, either from 2D to 3D, and also make it. This has been researched for many decades. People have, until probably 5 years ago, we once tried from my earlier classify those methods. We end up with, but we didn't publish because it doesn't make any sense. You'll see in a minute why it does. So what people have done is talking about alloy materials. We know alloy is formed by, and then the green steel, so alloy, take steel as an example. The raw meal, rocks basically, with oxygen and you burn them to 1400 degrees, and then they melt. It's not, and then they cool. During the cooling process, process kicks in, form some structures, and then you have it start to form grains concerning that process. Eventually, the transformation. So there are several visible processes occurring in that you could mimic artificially to build your microstructure. What people try to do, say using the so-called cellular automata, is a purely algorithm of different sizes, different orientations. I just box and then pack them to form. And by doing that, you might want to control your grain size distribution matches and your correlation function matches your descriptors, the path function matches your descriptors, etc. To your digital structure towards simulation. Phase field method is another one. It is a simulation method, but allow the input size to mimic the descriptors extracted from the reference. Transformation is a pure mathematical. So in this case, you could say, okay, the material, black and white, just two faces, is definitely not up and value everything. If you simply cut that, say everything above and the relation. So if we use the mean and the correlation and your only target. You could optimize transformation. It could be a plane, more clever, maybe a sinusoidal cut, but it would give you the same and mean of your reference. We did that 10 years ago. We are not a group who did that. This is 10 years ago was it has to be optimized, nonlinear optimized, but we did it in a semi-analytical solution. You to do that cut without. I'll skip this. The methods are you other characterization of just explicitly the synthetic model towards your you would face large language models, AI models, and the so-called generative AI have been so powerful in processing images. As this when we saw the video, this saw a woman walking on the street, all generated by the computer. So clearly, the algorithm, this can generate images or guided by your data, right? So as early as 2017, has become so powerful these days. Engineering tried to use generative AI to generate microstructure, and that was, I'd say, looking back, a step change. So the reconstruction suddenly become usable, and it's quite what I believe you can almost now previous method as traditional method. 2017 and ever since by several other groups. But the problem is until you do not know how well or how bad your reconstruction quality is, sometimes I say, and the papers only show you the good one. So what we did is we embedded us in this reconstruction process as part of the loss function. So standard VAE, you always have a loss function. Same as we showed before. You start an encoder to convert feature in space. This is of your how close you are getting to your target. It either doesn't convert, failed it, or when it converts, you know it's a good one for sure. There's no need to do about that. So, and of course, you need to train that neural network that more. Only so so there are two parallel discriminators. One discriminator, which is only considering the image, the inputs, and the other one we consider descriptors. And together they compete with the data. So it's like the traditional. You have two neural networks fight against each other, two on one side, one on the and this the result very encouraging. It is at least one order's magnitude. The standard GAN model, I am to that part. Whatever I do here, you'll get lost. But I hope the concepts get through. So how we use the macro to understand oil and gas sector. So they have spent a lot of resources to research largely to understand its permeability. For testing permeability, so you sample a little disk into that steel cell and then flow can only go through the pore. And then you run your fluid simulation, and then how flow coming out from one given boundary condition. So it's repeat, which was done. Its request requires experienced researcher. Is that possible? Use AI model here, so that you don't up to here, and then you get your result. It is possible. What that would that you then need to have your data set to train. Your data set would be, you should have many actions, and for each of them, you run your simulation probability, so you have that pair labeled for each of these probability predicted from your physics-based simulation. A lot of pre-computation. We tried that. Rocks we considered sandstone. Predict direct abilities. Labeled data, also descriptor. Your design space or your training data set requirement is lower. But the question is, examples of this descriptor function, relations, and those ranges that reconstructed that to understand which descriptors is the best one. Use the so-called wrapper process. Initially start with all these active descriptors, subset the optimal increase, and move to a conclusion. The next example is a bit more complex physics. It's about alloy, everything. So, reach the so-called processing structure properties and relationships for materials. The entire mass has been more or less researching. Always want to understand how the structure of materials it's like you start cooking with meat, pork, and vegetable to begin with, and you have your cooking process before it tastes like. Possible, or it's been researched over with engineering tools we now able to do, which include the microstructure characterization. We now reconstruct, have the capacity to prediction simulation. Say people say it's nearing general could be the laws of AI. Integration of models in science and engineering mathematics. Mathematics has all designed to be used by human and in that way to be used state of processing data to process large amount of data. That's possible to reasoning. That's true. Those tools have been designed for dataset processing. So the question, we do scientific reasoning through the data, converting that into something manageable. So that may require the proper doing things.
In research field. Any questions? The PowerPoint.
Yeah.
Yes. This in detail about how do you
I see. Okay. This standard is of variational autoencoder, and it has two neural networks: the encoder and then the second one. The first one encoder is simply the image of that vector as the data layers of a convolutional CNN into a vector mu. But we use the decoder, same structure as and then of course there are many ways to map it back. You have a loss function to optimize the parameters in your decoder, matches the features optimization. Have a dimension is space from both. So this is in the traditional here. Instead of using latent space, which is purely by the so-called encoder, we didn't use that. We call that simulation is essentially so we the image into descriptors, the features space network here, and therefore we only have it, and we still do the loop with the loss function to the image everything. So it's kind of consider this or the feature space is difference in our face understand in its intelligence as us. I hope.
Any other question?
It was a great talk. I learned a lot of training data, and it's expensive to get the training data in the material science. Some
It's a question of really need a lot of for using descriptors. If you only use the standard indeed you need a lot of training data. Image processing, all these you name by the data you have to integrate. The data requirement then becomes you can more so frame abstraction method, no more, no less. But again, require large
to describe these comprehensive centers of apertures.
Question gross mass. Full the only joint property distribution. As even use all of them, it wouldn't give you the capture for sure. But in the engineering, they have done, compared with experiments for good enough, I'd say, in general. And they are more than sufficient. In the literature, from 150 to 200 level, our accurate number in of my PhD student to analyze all of them. I tell right now because the work hasn't been. I believe a much smaller subset would be sufficient.
Thank you very much for the information.
Okay. We thank Professor Chen. Thanks. This tour began in 9:05.
穹苍千，物合多容，星黑洞冥冥。当探问宇宙的萌芽，照为基础，以为本。 肃的一理论计算机与信息科学项赋予机器逻辑推理的使命，成为基础自治的微智教聚会保障基础科学领域的重大为可好奇与探索之间，在等倡导下，比例基础科学大会聚焦临计算机科处学教师世界国界与文化的差异，搭建国际学术交流平台，探索基础科之未来。大会颁发基础科学奖和前沿科学奖。菲尔兹奖等团的抉择，评审准，这是要将之路指引方向，为人类探索未知世界照亮航程。
Over 100 people who have done their best ideas, and they come and they will be recognition of their work.
So basic sciences which will help all mathematicians, physicists, and this event.
I signed community. I myself looking forward to meet
mathematicians, physicists, engineers to come and get together to exchange ideas. So I'm looking forward to attend.
We are very happy together to the subject beneficial what a digital event that will be influential to the whole subject of fundamental science that will be beneficial to
从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学人类日月疆域，科学的人，这是一场低基础科广内。物和多种，云翠动冥冥。
I'm glad to introduce Professor Nestor from University of Lomé about philosophy. Thanks all.
Very much for invitation to speak. In the last years, with artificial our life and changes which create mind of historical remark. I think many of you realize that in the last decades, in the age of revolutions, so everything started personal computers. After that, of internet telecommunications, revolution, because all these new, so they need indeed advanced behind which actually will exist, and they are the main firms which are quite recent, and finally results in, I think, main event in the history of science. We can speak about birth, something started from, I think, demonstrated diabetes and all functions of considered as, but also human different solutions, and actually artificial intelligence is now born, and it is going to play an important role in our life for the many years in the future. The only thing which we can do is development in the right direction for us, for the. In order to understand how we were developing during years already, and general structure of the system of samples. So there is very special mathematics. It is an initial rule. So after that, there is a big exact science. Exact can predict the change like that. You see that using these sciences, the result of the sciences, so we can think and we know what will be the result. So we can predict performance of such things and so on. There is also a group of inexact sciences. Mainly can explain the past. This is history, so many really say why something predictive, and also so science which is quite special. This is philosophy is going to explain the interesting processes in our life. And actually in the beginning of the development of important. Now, it is not one of the main field, but the degree of remember the doctor. So this degree for the results in the usual system. So mainly this is the reasoning, so some convincing reasoning which work except maybe math, but in mathematics reasoning just to support that and so on. It's very important. In artificial intelligence, by which is really very, and this means so integral of, and this has already in this direction to computational mathematics. And note that this started more or less knowledge of intelligence was introduced. And when we objects are and theorems, so logical, and the results are very, you can as a goal of generalization. So playing things using them at the same time from the unique point of view and so on. This is classical mathematics. You can have many examples like algebra. Now, and this science is in this which has the monopoly for absolute. All other statements in any other, they have some probability that it is not in physics, but still, so maybe not true. Everything is absolute. This can be characterized very more. I think there are mathematicians in the audience that, yeah, they're quite many questions which come to the mind of mathematicians and answered. Now, question more prestigious is, so we know all this story with Fermat, with conjecture. The problem is to find the answer, and therefore, actually, many important problems remain. So they exist in form of high for years, for decades, so finally people. So and so on, and all of that. The pure mathematics, the time of the human life plays no ready to wait for him, and time that the objects are now mathematical models. Methods are numerical schemes which are implemented, and the result, you know, computational beginning of this new field. Many people results are computation. Computation speeds the life up now of computational experiments years just because the results of computational experiments become obsolete very quickly. So if you look at results of computational experiments, for example, 40 years ago, they in at all. So the problems are very small, tall, and so on. So with this mutation, they cannot serve in this field. So we see something. This theory mathematics long time. So today, so for example, optimization theorems on some gradient method were proved in 60, and they will be alive forever. So also computational experiments question which computational mathematics is computer also. It is not the mathematics to find a method to solve all problems in the world, so they do not. But we want to find a method which is a problem. So this is specification. Very different. Behavioral rules are also different. So the mathematics, the by potential application, all very quickly. Actually, just because we are trying to do that. Another. All the problems are solvable because we need to move, we need to follow the development of software and hardware and so on. This is very different. So this is another mathematics which is suitable for artificial. So in other fields, we can physics about computer example. All of that will be developed somehow. And by the way, so in many situations, so in this way, so the questions which it is impossible using the usual human intelligence. Okay, so sciences, so they should have been important for applications to intelligence. There is one thing for very difficult. Hardly replaced by something. Candidate for me, this is replace the structure of science. Okay, so the remaining part of my to explain true. So the classical persons, and for my goal, so the best person is Leonard Euler, one of the best mathematical brain which existed in history. Okay, and realize that nothing in the world whose meaning is very famous. And indeed, many principles of maximum for us or for as a specialist in also. So these two words place. So we should explain. This means that behind algorithm, there are always the minimum achieve algorithm, and for us it is interesting to discover them. So there are many examples. I think if you think a little, many other examples. So minimum energy of light. So Fermat law, consumer, which is important, and many. And the consequences there is the corresponding. We can say provide the target. And sorry, it's yes, and actually you can adapt them for the needs of artificial interest and optimization. Give a couple of examples or optimize. We start in type method, which the simplest problems minimal. So what we should do if we want to find the minimum? The gradient method is very simple. Linear analysis, general nonlinear analysis, is the direction of the maximal local maximal function. Yeah, this is the standard factor. We want to go in the direction of anti-gradient. We continue. Yeah. Extreme distance. It was 47. Did this so so you see this pure mathematician, famous mathematician. After this discovery, so of minimizing the order to be solved, what we need else. And one mathematician of this method. Yes, so beginning of computational mathematics, and this is so-called the heavy ball, okay, in this form, which was suggested in 1964. The interval again represent the friction inside the system, and this is it. So this is a version of this so-called heavy movement. where we look of our surface where 1990, the first look at the different years. The first to improve. So actually, indeed, so we can the fast gradient method, which is discovered 20 years. So let us look at its scheme. So the only is the point where we measure the curvature. Xk is in it isn't the predicted and our trajectory. So we have this is driving. Drive a car, we always look ahead at the position where we are. It is here. We forward allows us to all observe and run have some questions, and our job as a mathematician is to transform this into the mathematical statements. For example, what we can say this fast gradient method, so reasonable things for this is the worst case, how quick number of iterations. Yes, okay is the number of updates. Yeah, so we can look at that from the other. What is the best convergence? And this is given by complexity theory. In mathematical questions, the goal if I somehow support the optimization scheme and prove theoretically that it is good. Not practical application, but theory, which is supported. So now this style, so guarantee computer guarantee that the computational time is not good. So up to now it is not very common in the computer. Everybody knows this example. It happens always sweet to go. It is and what you are going to do are even intelligence and artificial. So all is about optimization. Again, do you know what inform this method? So after some number of iterations, so what we can about the quality of the art. This is not too big, so number of the field. So square one right digit in the answer. So after we had gradient method with this rate after 100 iterations. So it is already 84 fast gradient, 4 digit after 100. After that, silence, but which digit in 19 accelerated third order method which had the, and today, so the best possible 100 iterations, the digit of the answer. So you see, so this by they have required problems, and we indeed can have really very efficient and fast, super fast methods. Okay, so this is what optimization theory. Let me show you that we indeed have optimization. So the example of so-called intuitive. Actually, this is the question which should be people. Unfortunately, it is not, but they themselves. Of people you know, we know the great derivatives for the modern computers that people in the normal life come to ability to come. What is in the assumption? Assuming in the real life this doesn't happen, theory doesn't have any sense. Yeah. See, some algorithm words, simple algorithm. So what is it? It can be seen which so in this random search again, so it should be optimization method, but do not say what is the objective function. There's two parameters, which may be infinite and relatively big constant. Now, so our is characterized by position and so we get along the direction. So made on some tests. So we go along U with very small step. Look what happens with our compared with the step size. So this is our part. Quantity can be estimated. We can update our what we feel. we just function and we see is it good? Okay, estimate what happens if we do. Yeah, so we can do that. It is positive, which means that the goal is supposedly to be. This is bigger than that, so our use. So we go with the big step. In this direction result the opposite. Now, which is good. Go again with very big step. Yeah. Something which, from the common point, quite strange. Yeah. Not too small experiments, local experience changes. Yeah. So we see if it was we are not to think more and so on. But it appears that this is enough to have enough. It is not for the function f. It is for another function. Method. And we speed random perturbance, small random, which we want to be in the position where all these random performance so are so we don't care. This it appears that for this process objective function, but the method of minimizing function, which this ID function, but its behavior by it, so he minimizes. Behavior is predictable. We know will go such random perturbation. So in terms of know that need actually on the level of feeling, intuition. Sure, it can be implemented if it is accessible. So cats, so what they have exactly like that is bad for them. They go in the opposite direction. In this direction. So it explains situations. Animals are also rational, so with intellectual. So I think that also at one more the real life solve some with that data. So some I don't know type of problems which are caused clustering. Clustering actually arises in many different fields, only in the computer science, so it arises in many. Do some classifications. We have the setters in M dimension. To some centers of the clusters. Several centers of the cluster, so these variables to k, which are close somehow, so people looked just in the beginning, so standard way, standard strategy which exists purely engineering. So we just do without thinking too much about the complexity of computation, and after that we run computer, and it's of course not very good. But let us look. First of all, the attachment mechanistic, but you can participate in different centers or in different activities if you want. So what SPI should be? So don't ask me why. So the probability high. So experience, people decided that this is a nice formula, and of course for generality they add some parameters called falsifier of the system. How to choose it? Therefore, normally people do. But anyway, so we of this position of the center. Objective C the position of the center, and we minimize it. So what is so the probabilities multiply. Okay. Unfortunately, from just because that so the functions on our variables no structure at all. So they have many local solutions. So optimization methods applied to this only local solution, no hope to find a global solution. Somehow from this minimization, of course, with clustering, but nonetheless, next is one of the and actually what is the answer question? So can we indeed presentation models like which have the unique solution? Important to have a unique solution, and then we have difference. The solution. Okay, so just but how to improve it, how to advance in this direction? So from our philosophy, we just need to take a successful life situation. Yes, successful classes in our nature, whatever, for a time. So this is really good. Our goal, actually, special elections in the United States, main candidate nature in democracy. theoretic consequence. For example, so example of the different people, different. So in accordance to the preferences and so on. So let us try to model this. Okay, let us try to model this process. Try to create the voting model, and we will see actually how it works. Yes, so let me do that right now. Just everything is evident. So participate thing. So we're going to several parts. Yeah. Assumption is that result random. Random means that we party, but they exist also non-zero. Maybe this probability consider continue distribution of. So let's introduce party K with some probability. Okay, so of course the sum of these probabilities are equal. Pi belongs to the simplex, and this will be the result of yes. So this is the vote. We know personal opinion. This. Now, what also is not important is the position of the party. In party, okay, and they're flexible because the parties can change the now, and the position of the part will be the output of the. Now, so we need to describe the case, so how we compute the probabilities to vote some position. We need to introduce some distance in the space of features, and intuition is that the bigger opinion of voter and position of the party, the smaller is the probability this guy selects this party. But it is not zero. Let's write it in the following model. Here you see the party I. Okay, smaller is the probability, so on. So this is a classical logical logic monomical. Okay. So probability x which go zero, so we get deterministic choice. If mu is strictly greater than zero, then we have some flexibility. Now, therefore, actually, if we know the positions, yes, x, k are the position, no problem with that. The problem defined now is that we have to defend, and these basic principles are all space as the opinion of Position can be different. They see the let us listen of the party to the opinion of the guy by the probability that this guy is going party is the probability is 0 about his opinion, and we compute this average distance. Minus the mixture of this average. D is the distance function. There are some, and so what is there again? So here this paired somehow with the volatility when gamma equal to 0, the position is always equal to 0. So they have this is the model. Okay. Now and doesn't matter. So the solution of this minimix case so is unique and so on. So now we can see the process. Modeling is finished. Now we can. So what is the position? We make voting, which means that using these probabilities we update position. Very simple. Yeah. Yeah. So say present election and analyze this mathematically. So it's a meeting point. Okay, as it should be. Yeah. Which has unique solution. So, but note that so the two parameters. So the volatility of the level of conservativity is gamma. Yeah. It's smaller than. And moreover, so this process converge very, very near rate of convergence. So it converges to a single. So the auxiliary problem is for part of work in order to get. So interpretation actually also is a very nature. Parameter mu is of the waters, and gamma should be smaller than 1. Means must be more consistent true. Then our avoid too much of populism of the big party when parties follow company of the population, it becomes unstable. Need but now so it's history be more the main yeah, why we are speaking about optimization, but because actually there is optimization behind. So you don't don't see people which vote and parties which change their position about the optimization behind, but there is, here it is. Convex function. So it is minimized. So we fix xk. This is again a simple computation, but for minimize this, we get the probability of optimizing it improves of the part. So we divide our groups, we fix one group, minimize it, and then minimize the first, and so on. So methods which one example we yes, so this approach and the rate of convergence is important, which means that the game from game theoretic game. That's one of and very difficult to realize that in fact, so these behavioral processes are just minimization methods for this potential. Okay, and I come more or less to the conclusion. Optimization theory processes in nature, life, and I different more in many, they can be formulated. On the other hand, so they the people apply life optimization. So this way so provides us with a method predictive power of the try to predict the results of elections in the United States, but next time maybe I will have time to collect information what is going on, because up to now, and you know this, we cannot predict well something which this will be the result after we apply. It's only the beginning of the process. Beginning of the process, so many fields being more and more computational, and this will play to see Dr. outdated. Thank you.
Computing philosophy is very super. Thanks a lot. And so, any question?
So you have an excellent example. transactions, interest, say,
is changing. So many waters they can be by that, but at least basic do not which are so this you see here. So but it is a summation divided by n, which means that so it has some properties, and you don't need to ask all of it to do survey, and you can have quite. Of course, nobody says that, but this is a proof that, and again, same for Watkins and so us that actually, so all of the people close the eyes they for themselves in the paper. And so this is a actual and something paper. Only the correct measurement can help, and I think that this really is because we know, of course, the political system are not stable. So this algorithm is not applied well. So no, there are many cases that
I have another question. So you mentioned the method. Well, these methods work on the like mirror descent. And we only discuss like the gradient descent.
No. So this is the difference. Curvature run. If you move function for speculation, this is theorem, so we can prove this. Mm-hmm.
Okay, in philosophy field, always need to look for lies there as
in between. Well, again, so the concepts of optimization so 100 years in economy, do they behave? Solve this problem when people are irrational. So the wrong. So they do not make mistakes, and they are absolutely rational when they behave conscious way. Okay, you think or think about something, move along the corridor, whatever. This is we need to predict subconscious behavior. Or there are many situations like that. For example, when you go to the shop and you come this, and this is it. Without all these computations, so I do my. But this means that computations were done. Okay, and it is possible to transfer in the algorithm, and we can. So we have very much.
So we thank you. And the next session will begin.
“穹苍广而恒间，星云璀璨，基础和照世界。数几何根数学考重塑了人类对万物的认知。物理学家以会一系推水，夺取无数希望，推动人类的飞跃。只记过句号。必治愈的，为科学家至今在求愈合。国际基础科学大会应运而生。大会聚焦数学、理论计算机与信息科学三个领域，邀请全球接界学问之大流，跨越国界，搭建基础研发基础科学终身成就奖、科学奖、世界多国菲尔兹奖等奖项得主。组团现中立持正等流程，为青年迈上研究之路方向，为人类探索未知这样航程。
We chose over 100 best work in the last 5 years. They presented with some award for that.
I want to greet this July. Combines every great success.
Event for scientific community this year. I myself looking forward to meet many top researchers.
The opportunity for mathematicians from around the world ideas
to mark the fourth one to human. Make that a standard for the science. This will be a very successful event to the whole subject of fundamental science to all human beings.
古至今，已有的科学类。是的，这是一场顶尖的智慧交流。我们以基础科学之光，点亮未来。千物合多容，星云璀璨，动冥冥。探问宇宙，藉此照亮蒙昧世。即学好重塑了人类对让我们掌握不可思议的能量。理论计算机与信息科学家以赋予机器逻辑推理的使命，一招开获时空文学托举无数希望，为下一次质的飞跃。风雨与君有彰基础科学领域的重大进展，为科学好奇与探索之精神，秉承开放与合普科学大会数学基科学，邀请全科学家研讨世界学问之大，追寻前沿科技之深邃，搭建国际学术做基础科学发展，基础科学终身成就。是能讲得邱担委员会主席，则严格遵照平国际基础青年上严厉对探未知
People who have done their best work in the last 5 years, and they will a recognition of their work.
I want to greet basic sciences which will be held in Beijing. This is mathematicians, physicists, and computer science.
I think it is this year. Many topics.
This is physicists, engineers around and get together to exchange cutting edge. Forward to attend all this exciting.
Happy to see the best to discuss the physical things. The best paper award will be influential to the whole subject of that will be beneficial to all human beings.
从古至今，之科学家力中的宇宙，基础科学不断拓宽人，这是这真的是让我们以基础科学之光，地的未来。广和明明论觉由此萌芽，照亮蒙昧世界。万物之理，数为基础，方程为本。
to July 世间业 to begin his talk about the effective and adequate theory applications. Thanks. Okay, welcome.
begin by explaining my title. The word very often in recursion means just I'm using, if you design an algorithm, it's effective, implemented, and have the properties. And to be able to implement out that converted is Turing computer. Define a lot of algorithms used like real and zero. Not effective means you want algorithms which really can be proven to be Turing computable. But means, well, you need tools. You can very often prove that certain algorithms, but you may not be able to do an example today about roots, finding roots of polynomial. Yes, but we don't know how to equate theory of real computation. Okay, so let me begin. So bear with me. The structure, and then I'm going through optimal root plot and Euler's method, tracking a homotopy path. And then talk about how using these from the algorithms you design so that you can really algorithm out of it. We do so your construction of the real number line is the foundation of Dedekind cuts or Cauchy sequences. Is this? Some of you probably know that. Years ago, I was very struck by small analysis. Trying to understand the point space, right? And there's a lot of debate. The atomic view did much later, but the continuum is still there. Read the code for yourself, but this point may not be considered a part of a line. So of Brouwer, Renato, again I'll quote the shortest one, a true continuum. So continuum is the name. Okay, topology. Okay. That yes, there can see from tensor analysis where you work. And for us in interval, you know, there's a world of computing called interval arithmetic, computing as if you're working with numbers. To me, that interval methods are absolutely essential to design effective algorithms. Keep that in. And then from Caucher, Schub, and Smale manifest Marx has a manifesto, right? Workers of the world arise. This is what we have to do. And they were called a modern scientific computation. Well, the Turing model is out that mathematical, so we propose computation. The real random access, where you can manipulate real numbers as individual, solid, atomic wholes. You can check whether a real number is 0 or not and branch. They also complained about built in the 1930s, complaining that is too and so in that book. And you're going to hear the word soft a lot of time. And this is my way kind of ideas. Soft heart. Is soft. Who have background, theoretical computer science, where you study theory of computation, complexity theory, P, NP, completeness, and so on. Complexity theories have been the theory of complexity for the numerical and the CT. Here's an impression. What is can you? I'm not quite sure. I give you rational computation of P over Q. So last bit you can slash poly and pieces. The slash poly complexity class is very high. Listen. Numerical analysis. I gave a one. Okay. We can analyze algorithms, but usually the number is it. Well, if the hence the algorithm does so, it's and for theoretical interesting algorithms that doesn't so once is called, which is predicated on an extra whatever algorithm you have extra. You spend and compute station. Oh, that's it. If every arithmetic step be arithmetic by your hard IEEE operation is correct until the sequence a bunch of operations paragraph sequence. You get every bit garbage. And this is not easy. I hope this is a very good solution. I've been working on geometry EGC for a while. We did a core library. Fun that I had, you have to decide zero and zero. Your values the positive and the other decide number all signs. Don't have to compute with exact numbers. And we can do in 2000 according to each. The draw theory, I still love it. And you have bounds. Problem with zero. We always you can trip condition zero. And you can even know where to stop. Just the zero. Most of the work in outside approaches. So and I realize is that we don't really need constant physics accuracy. Worst. Correct. Worst constant. We only always provide the definition of algorithm. Meaningful. Okay. Even the shape of everything. So we talk. Became the condition. I need to really idea real computation. That's all that. And theory from top down. Understanding of ability. I look in hard to solve properly and see what the technique. And in each case is the first. The structure of my talk. So we theorem of basically non-multiplicical roots. TAA, the second fundamental algorithmic part means basically in 1981 from short paper has never been highly picked upon and other people. So by the I tend to believe in this result. Isolate all roots of a polynomial. Of course, means 40 is a power of 2. How we get algorithm. Static. Polynomial has then the O tilde n squared, and basically this is optimal examples, and we say this is basically the correct picture. So we know I have to clear what the benchmark problem. Complexity theory is like what's the one root? Find all whatever. The simplest says and that's what I that understand it well where because basically we move it's like multiplied the divide use big integer or Java, then we move more different and root isolation now in that fundamental assume in but they are all well numerical and but if two roots are very close, wish them. You don't know is it the same thing? Weak and computer algebra no, sorry, root isolation. Disk that contains that if there are multiple roots, but you have to tell me the multiple root. And once you want to arbitrary fairly, so we don't even talk about that. So this is getting the topology. I want that. Twist and turns from basically that this how we turn into and implement. And for a long time, but whatever people in the world. The new that most of them are direct. Guarantee algorithm. Computer Maple, Mathematica, they like if you are using term sequence, find the complex less, but finally using subdivisions and 2018 I'm involved even for complex search we can do it and fairly different. Both these techniques that he linked with the idea simply give me a polynomial. The first thing I do compute two whose product polynomial, but these techniques are soft ingredients. The first is what I could again isolate number of roots in delta. If that's polynomial, of course, you take the you and equal. So any set of roots inside some delta, but if it is well isolated, cluster. So for blue, green, cluster, right? Those two include the green root, right? Blue cluster 3 times bigger. Like there are simple reasons for that cluster. Any either is joint contain they cannot just in partial, and therefore any general cluster they only can form the cluster. We think very famous test called palette. He said so if you're giving a polynomial, if you are familiar with this sort of splitting it to and Artur and all this is a very famous number of roots. But see, what I call in logic we have predicate. If the predicate, then it is false. Only 2 friends. Seeds has fails you. we really need a partial converse. If it does succeed, can do it, and if the disk by over 11 times in there, and cube roots succeed. That's only how can you polynomial f, you can do, and the point n times capital, then the roots are exactly the original roots, but exponentially. I mean, not the unit faster one. And those are away. And so here is the geometry of the circle and maroon or circle is the smaller circle is bigger. There are no roots. F expansion, we make it, now it's, the box does not easy. B to this circle, then if and no roots in region, and if it fails, well, then somewhere in here. So our main right. I'm not very good at that here. Describe it however you want to do it. This is what I call soft. Now you have how much time? It's left 30 minutes. Okay, remind me again. I have the motion planning. So you want to move, avoid, and picture angles, and A is this point, three logically different paths. This is because it's a wall, perfect, whatever. So you can plan, make, okay. We don't. this kind of the map locate and down in path problem. Look at the job search. Early AI, at that time we were just learning about search. There's this exact the sampling approach, robot implement, you just do random, and this is a code from a different kinds of sampling out here. And planning performed for high-dimensional robots. Wave problem. This is a book. The it doesn't. I go into familiar with these the robot R3 as of position based. That was it's a map. The foot maps configuration where the footprint of the standing. Here is so that map is what the obstacles. Those free from empty maps you for path hitting the bound the obstacle. Okay. So here's the exact alpha either output a path or you output no. This is required. The generic. I give you omega alpha beta and resolution is possible. Sometimes I can or output of sessions. K, which is positive, say K, and if there's a path of clear, you okay. To make it okay. So if there's a epsilon over is not because the epsilon over 2 and 2 times epsilon both are okay. Consider an answer. Okay, resolution. Exactly. So now your end of time. Just tell you that working on years, and we're all kinds of method weaker. Some out of you define a path clear. This challenge in here. Robot and of freedom. 3, a rigid body has translation and 3 degrees of rotation. Complete. We're in the process designed it. This has worried people for a long time. So physical space. So in this case, but a certain very so no is in SR3 for those 3 matrices represent, or you can 4 numbers and numbers. In fact, you will use and rotation. But this is non-Euclidean. And I'm going to just, so you're trying to find in this square what is this, and it's a final alpha to beta. So a bit hard to rectangle. This is so simple. It's a space. That's about the time you get what is a disk. Boxes. Green. Red. Every point in green means yellow means well, or maybe it's yellow. So sure. So red, yellow, and this is in 3D. Is it presenting it on 2? You can think of wall, blender. The color with yellow, green, or red, them into some and highlight. are doing. In your space, one green stuck in some freeze, throw it away. We're doing that. The subdivision, what I call search. While the queue is not empty, you just that you split by the green, red, you're done. If it's yellow, and you prove that this is correct. Question. Okay, I add this. We're trying to offer to you is the idea not classifies that's clear. The classification of C tilde. This approximative it makes that really is green. Is really yellow. And it's converged. Does converge to the correct answer. Soft version of the fourth row very SE3 row, which robot in theory try to do a rod array, and this is to try a robot. This as it could be can unions of algorithms for doing algorithm design. Challenge we have is in how to so viewing it as a quaternion with three-dimensional and view the boundaries of the four. There are 8 cubes. The four, so 3 the adjacent for cube. We have to produce the different charts and to get information out of. So how 15 area getting clear up. So and this might the root of a polynomial f equals, and what you do is you h of time minus x polynomial for which usually Tf. So you have the roots of you take any of them and try, and typically you'll be n minus the units roots of unity. So path, well, here's the curve here, and you move green point, which is outside. This is ideal. You don't in reality even hopefully not keep exact. If you wrong in this zigzag things, the roots mentioned. Best EHC form. The state of the from the book of Somesi, introduction algebraic geometry. And point. Okay, and you the determine R, and then you have max what I'm trying to find roots, these things. Why am I going to figure out what to give? But you in computer science, we said it's not a mind students. What is not algorithms? Very powerful. What you get. You look so human and ago people just came up with a way to path, and it's if you will in my view, in weeks of pattern test that I talked about, this notion is Smith's alpha criteria. Point to get to the final point. And the point, very sort of a very strong property you get from this test using our soft palette test is that now you can refine your well-isolated disk. For instance, if this circle is a well-isolated disk tracking your root, so there's no roots in a bigger circle 3 times. Suppose you say, well, I want to shrink my well-isolated test. Well, you can do a simple subdivision. You form a square, circumscribing square of your disk, split into 4 sub-squares, take the center of each sub-square, do a test, palette test on each one of these smaller circles, and you can show that each one of these smaller circles is well isolated also, because if you take this circle and make it 3 times as big as this one, it's still inside this larger circle, so there are no roots. You don't get any new roots. So it's well isolated. And so if this test is well isolated, one of the 4 will, at least one of the 4 will succeed. So now you have shrunk your test. And this is very powerful, very powerful. Nothing like this well, I don't want to go into the geometry of good homotopy. Basically, as you track the path, let's say the path is alpha of t, it satisfies this equation, the h with, and if you differentiate with respect to t, you get this. And now you get an expression for alpha prime, the derivative of alpha, and it's equal to g of alpha of t at t, which is this expression. And this expression, if you plug it back into this, is this very nice rational function. And basically, a good homotopy means this guy doesn't vanish. So at every point you have a direction to go. You cannot vanish. You cannot go to infinity. And this must not be 0. And now, so let's say that you're trying to track. At time ti, so I equals 0, 1, 2, 3, and so on, we have a state, which is sigma sub I. M is your current midpoint of your well-isolated disk. R is the radius of your well-isolated disk. Ti is your current time. And delta I is like, an estimate about how big a step you're going to take for the next time. It's not very critical, but you should have something like that. And if you have a state here, which is a disk, and the next state, you can take the convex hull of these things, and it forms a frustum. And this frustum, hopefully, you know that your curve comes in at this end, and you want it to come out on this end, right? So this is a valid frustum if true. So how do we ensure that? Well, so if you have a sequence, you may be forced to shrink this frustum, and we already saw that palettes well-isolators allows you to shrink, actually, if you want to. You shrink it so that you can get the properties you need. And so you form a funnel chain, a chain of funnels like that. This is what our algorithm will produce. And typically, people don't analyze very carefully. The predictor, corrector, right? The predictor is usually not so important. You just take a step forward and hope for the best. Corrector means you have to come back to this. And this is our corrector. And notice that you come in with an expanded state, because what you hope at every step is you want to keep expanding. You want to take bigger and bigger steps. I have 5 more minutes? Okay, thank you. And it turns out that you need to check several things. For instance, the first thing you ought to check is bounded. This is that you're in a good homotopy, that condition within the frustum. And if it's not, you have to go to corrector number 1, and you go out again. You have to reduce your state. But if it's yes, you go on track. On track means is your curve coming out on the other end? If it does, then you're okay. You don't want the curve to go outside to the side. And if not, then you have corrected in a different way. And finally, you want it to be well isolated when you come out. And if not, you have to correct it. So this is the structure of our path tracker. And then, so this has a loop in there. We call the inner loop. You have to prove that it terminates. And then in path tracking, you have the outer loop. You know, take step, step, step. How do you know you're going to end up in the final place? That's a bit more subtle, and it affects how good your algorithm performs. So I ran out of time. I have this, what I call pathway to effective algorithms. And it's based on another paper that I worked with Su Qian from Chinese Academy of Science, where we designed an algorithm for finding roots of a zero-dimensional polynomial system with isolated real roots. And we want to find all its roots in a box. We want to certify algorithm for that. And of course, we do subdivision. And you have predicates, tests. The main predicate is, there's a predicate basically based on Jacobian test that tells you there's at most one root. And then there's another test called Miranda's test that will tell you that there at least is one root in there. It turns out Miranda test, you have to do some preconditioning called Moore-Gostelides test so that you always will succeed at some point. And then you have these predicates, and we define all this exactly using mathematical terms. I call these predicates C, the ideal one, C of any box. You have several of these predicates, but no one can implement this correctly. So we have to use interval form. So I put a box in front of C. So now you describe them as interval methods. And then effective, the interval, well, intervals have ideal endpoints. You really, in the real world, have to round it to the nearest machine representable number, maybe moving out a little bit. So you have to take all this into consideration. So the point is that at every level, you make sure that your predicate, the tilde, if this is true, it has to imply this. If this is true, it has to imply this. And at each level, you prove the correctness of your algorithm. 3 kinds of algorithms is correct. And usually, the move from one sort of minimal, only certain things needs to be taken care of. But the structure is very clear. And I propose this is the right way to design correct, certifiable, implementable algorithms. You have to go through all these 3 steps. They're all useful. It would be very foolish if you say, I want to solve this abstract problem. I instantly go to this. Nobody will understand what you're doing because you've lost every structure when you go to machine precision. So I call this the AIE scheme, A for abstract, I for interval, E for effective. In conclusion, well, in the last 40 years, we have built up an arsenal of computational tools for algebraic computation. Basically, we now know near optimal operations for multiplication, division, GCD, now root isolation. And from now on, you can use that to build other algorithms, right? Because they are basically solved. It's library, call from the library. You don't do any research on that anymore. Root isolation to come to this point. I would say for the next 40 years, to do the same for certified numerical computation, the kind of algorithms I talk about, we need an arsenal of soft tools. And basically, as I'm working on these concrete problems, I found that the tools are not there. I have to invent them, right? And I encourage those of you who are interested in algorithms to really look hard into what you do. Don't trust the algorithms you get from the libraries. They usually are just, well, it's good enough for a lot of purposes, but not good enough for certain certified computation. And the way that we uncover the needed tools is by attacking the challenging problems, a bottom-up approach to theory building. And if I look at the history of what people have tried to do in the theory of real computation, I see a lot of missteps. And that's because they're building theory from top down. And then they face the reaction of numerical analysts and said, this is nonsense. This is not what we are interested in. You're not telling anything that's of interest to us. So we want to make sure we build a theory that's actually relevant to practice. And the underlying foundations for this will follow, hopefully not prematurely, but I understand a lot of the elements that has to go into it. And there are lots of other ideas, related ideas like set value analysis, multi-valued functions, functoids or ultra-arithmetic, or computing with functions. These are various groups working on different things, but they're all speaking to the same concern that I have, trying to build a theory of real computation. All right, so I'm sorry I went a bit over.
Thank Professor Ye for the excellent talk. So questions?
Everything is clear. All right. Yeah. Oh, I think I have to use my. Oh, I think I'm fine. Yeah. Go ahead.
Thank you for the nice talk. Sorry if this question is too naive. And trying to eliminate all hyperparameters. So one question I had is, you made choices for kind of the geometric shapes for how you would say applying, say, pellet test or something like this. But what if I didn't pick, say, just a disk? What if I had picked a more complicated geometric object to?
No, I'm the algorithm. I designed the tools and primitives to solve your problem.
Yeah, but we could decide that we wish to tune the geometric shape. Maybe squares are better than circles, or a flower shape is better.
Okay. Well, then, yeah. Okay. That kind of algorithms of hooks and all kinds of parameters, hyperparameters, and but the bottom line is, at least you should have the ability to solve the problem without asking the user to give you any hyperparameters. That your solution does not depend on the hyperparameters. In our SSS framework, for instance, we allow you to choose various things actually. And one of the most important for this finding path is the search strategy. I said the search is very simple. You put all the yellow boxes back into the queue and just take out one using some priority. What priority do you use? You can use random, you can use breadth first search, you can use depth first search, Voronoi heuristics, and that greatly affects the performance of our algorithm, but it does not affect the correctness.
Thank you.
Thank you for those questions. Any other questions? Okay. So thanks for Professor Ye again for his great talk.
Thank you. Again, the slides are available, right? The slides will be available if anyone wants. Okay. Yeah.
Thanks.
Send me an email if you have other questions.
So this is the end of all the talks of this morning.
So, okay, talk, right?
穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开阔，时空时维。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕姬， 群显毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在丘成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、理论物理、理论计算机与信息科学三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。
So what do?